I'm going to go all out. Okay, so I'm going to do an example of a two-body problem with the central force. And I'm going to model that with one dimension, and that's this r value. So I've already derived the bulk of this. I have another video. I'll link that down below. Okay. Okay. So, but here's the situation. So if you look right here, I have these two masses connected by springs on like a frictionless table, and they're rotating around with a spring connecting between them. And I want to model the motion of this. I'm going to actually do it two ways because that's what makes it fun. I'm going to do it with a central force equivalent one-dimensional one-body problem, and then I'll do it actually with two masses connected by a spring in Python. So I'll do it two ways, and hopefully we'll get the same thing. I'm not 100% sure everything is going to work, but we're going to do it anyway. Let's go ahead and get started. I'm going to turn off this camera. I didn't turn off the camera. I locked the camera. There. Okay. So let me move the microphone a little bit. Okay, so I have these two masses, M1 over here, M2 over there, and they're rotating around in this flat plane. Now, in order to do the central force problem, and I picked some parameters up here. So let me describe the central force problem, and then I'll start calculating stuff. If I have two objects like this with a force that acts between the two, so this spring only acts in a line between the two, gravity would do the same thing, then I can do a couple of things. One, I can use the center of mass system. In the center of mass system, if the center of mass is at the origin, which I need to make, and the momentum of the center mass is 0, then that reduces the problem to 3 dimensions. And then if I say the angular momentum is conserved, then I can get that down to 2 dimensions. And then using the Lagrangian, I can actually make an equivalent one-dimensional problem. And that's what this is. So in this problem, I have the reduced mass mu. So this is mass m1, that's mass 2. The reduced mass is m1 times m2 over the total mass. Then I have the angular momentum, which is a constant, and it's the reduced mass times r squared. R is the distance from one mass to the other, and theta dot is the angular velocity. This is actually the total angular momentum in the z direction, so we can actually find that as, because remember, L equals r cross p. So I can find the total angular momentum for the system and make that my L, and that will work. If I don't want to find the angular velocity, I can do it this way. Once I do that, I get the following from the Lagrangian in the r direction. This says mu times r double dot. This is like ma, right, in the r direction. It's equal to L squared over mu r cubed minus the actual force, the central force, the derivative of the potential with respect to r. Now you may want to go back the other way, and I'm going to do this first, and that's to say, well, what if I just make this like a potential and combine it with that? Well, if I do that, if I integrate this, I get this. So the effective potential is the centrifugal potential, L squared over 2 mu r squared, plus the actual potential. And then I can treat it as a one-dimensional potential problem just by adding in the centrifugal potential. Okay, so that's what I'm going to do. So here are the parameters I have. I picked some values. M1 is 300 grams. M2 is 100. The spring constant's 10. The initial R position is 0.12. And I put this V2 is the velocity. It's going to be initially moving just in the perpendicular direction. So let's call this the x-axis actually. And so that means that R0 is that's the position at time t equals 0. R0 dot is 0. The initial velocity in the r direction is 0, but not in the theta direction. And this is a spring with a 0 length. So if it's a distance r, I can write F is negative kr. That's the spring force. And then I could write the spring potential as 1/2 k r squared. Okay, so it's not a realistic spring, but we can make non-realistic things. It's really easy in physics. I know that's funny. I thought that was funny. Okay, so what do I need to do? How do I need to move all this stuff into this stuff, because I could solve this equation. The first thing I want to do is plot this, right? I want to plot the potential as a function of r, and then I'm going to use numerical models, a numerical method to solve this differential equation. Okay, so the first thing I need to do is to find L and mu. That's it, right? I need to find L and mu. Mu is easy, right? I'm just going to take m1 times m2 over the total mass. That's done. Easy, easy. But what about this angular momentum? So let's redraw the picture. I need to find the angular momentum, and that's not quite so trivial. So let's say here's mass 2, m1, and there's my origin. This is m1, m2, this is r, this is, let's call this x1, let's call that x2, because it's on the x direction. I need those values. So if, let's do the easy part first. If this is v2, then that's v1. It has to be going down. I have to have the total momentum as 0, so p total equals m1 v1 vector plus m2 v2 vector. But in the x direction, it's not moving, so the momentum in the x direction is 0. So p total y is going to be m2 v2 minus m1 v1 equals 0. So v1 is going to be equal to, add that to the side. I'm already just find the magnitude. It's going to be m2 over m1 v2. So now I know v2 and v1. I already said what v2 was. V1 has to be that. Okay, now what about the angular momentum? So L, and this is just the z component. LZ is going to be x1 times this momentum, which is m2 v2. So they're in the same direction. So plus x2, and that's x2, x1 m1 v1, right? Because this is equal to r cross p. So r is this distance, p is perpendicular, so it all works out just fine. But I don't know x1 and x2. But I do know the center of mass has to be at the origin. So I can say 0 equals x1 m1 plus x2 m2 over m1 plus m2. That has to be the case. And I made a mistake here. x2 is actually going to be a negative value. So this is, let's call that negative right there. It's going to work out, trust me. I really could write this as a vector, and I will. But I need to find x1 and x2. That's what I want to do. So I can multiply both sides by the mass, and I get x1 equals, just solving this, equals negative x2 m2 over m1. Now, I also know that r, this is going to be x2 minus x1. Wait, why the heck? I did this backwards. That's why. That's why I was getting all messed up. That's 1. That's 2. Okay. Because that's the displacement. From here to there is this value minus that value. So if I use this and solve for x1 equals x2 minus r, I put that in up here, I get x2 minus r equals negative x2 m2 over m1, and I can solve for x2. So I'm going to get x2 times 1 plus m2 over m1 equals r. So x2 equals r, which I know, divided by 1, which I know, plus m2 over m1, which I know. So now I got x2. Now I can get x1. So I have everything, right? So I have, in this formula, x2, I have that, based on r and then the masses. The mass I have, v2 I have, x1 I have, m1 I have, v1 I have. Okay, this should be a positive number, though, so I'm going to make sure that's positive. So now I can calculate L, right? That is L. And then I'm done. So now the first thing I want to do is calculate the effective potential, EFF. equals L squared over 2 mu r squared plus u of r. Okay, let's do it. I'm going to switch over here to Python, and so we can start doing our stuff. I'll probably have to switch back at some point to show you how to do a numerical calculation, but let's just make a graph. Okay, so switching over here to Python. Python, camera present. Computer view, there. And then you have my picture too. Okay, let's just start entering in some constants here. Put my paper right here so I can see it. And I'm not making a visual thing first. I'm just making a animation. So I'm going to say M1, oops, you got to be in here. You can see that. Okay. M1 equals 0.3, M2 equals 0.1. I converted it to kilograms. K equals 10. I'm using lowercase k. R0 is just going to be R, right? Because I can change that. Yeah, let's just do that. R0 is 0.12. V2 equals 0.2. Now I can switch over to the stuff I'm going to calculate. Mu equals M1 times M2 divided by M1 plus M2. That one's easy. Now I need V1. V1 equals M2 times V2 divided by M1. That's the magnitude of the velocity, right? That's because I've already taken into account the direction. And I know that I did that a little weird, but that's the magnitude. Okay, now I need to calculate x1. x1 equals I did x2 equals r divided by 1 plus m2 divided by m1. And then x1 is going to be equal to x2 minus r. Okay, let's print x1 and x2. I don't trust myself. And now let's run that. Let's save this as rotating spring graph 1. I don't know. Does that sound okay? And now I'm going to run that. Okay, so that gives me x1 is negative. Okay, that seems good. Now let's do one more thing. Let's say r equals, this is the center of mass. It's going to be equal to x1 times m1 plus x2 times m2 divided by m1 plus m2. And let's print that. It should be 0, right? That's how we solve for that. But it's just working backwards to make sure that we're not crazy. That's 0. Okay. I know it doesn't look like 0, but 10 to the negative 18th is 0. Okay, so I can get rid of that. So that's working. I can get rid of that. That looks good. Okay, so I have now let's actually make these as vector values so we can actually calculate the vector values. So I'm going to say P1 is going down. So it's going to be equal to M1 times vector 0 negative V1 0. P2 equals M2 times vector 0 V2 0. They're in the y direction. Now I need R1 is going to be equal to vector x1. It's already negative 0 0. See, that's the thing I made a mistake. Some of those are negative and some are not. X1 is negative. R2 is vector x2 0 0. Now I can say L, which I hate L in Python because it looks like a 1. It's going to be it's going to be the magnitude of cross product of R1 cross P1 plus R2 plus cross R2 P2. And let's print L. I don't know why, because it won't make any sense. Okay, so that's my constant L. Okay, so I got that. Okay, let's plot the potentials. Let's plot all three. So I'm going to say T graph equals graph, X title equals R, in meters, I guess I should say that. Y title equals energy in joules. Now I need 3 graphs. I'm going to have one for the centrifugal, so FC equals G curve. Color equals color dot green. FK is G curve. I guess I should label these two. Color equals color dot blue. Label equals spring potential. We'll call this label equals cent pot for centrifugal potential. And then FU is going to be G curve. Color equals color dot red. Label equals effective potential. Now I want to plot these values, but I need to start from, I can't start from, if I let R equals 0, I think bad things happen. So let's say R, I'm going to use a new variable RT because I don't want to confuse it with that other R. RT is 0.02, 2 centimeters. Let's start from 2 centimeters. We can change it later. And then dr is 0.001. Let's try that. And so while RT is, I'm going to move RT up to, let's go to 0.2. I'm just guessing here. Okay, so the first thing I'm going to do is to, I just need to calculate my potentials. So UC equals, where'd my thing go? I wrote it down. I don't memorize these things, you know. It's L squared divided by 2 times mu times R squared, RT squared. Then I get UK is going to be 0.5 times K times R squared. And then U equals UC plus UK. Now I can plot them. FC dot plot RT UC. FK dot plot RT UK. FU dot plot RT U. Now I need to increase R. R equals RT equals RT plus dr. And then it should increase it. Let's save this. And I'm going to turn off the picture of me so we can see the graph better. Let's see. Bye. And run it. Okay. Something happened. That's not what it should look like. Okay, so 1/2 kx squared. So the spring potential is tiny. This, what happened to that? Oh, I did 1/2 k r squared. Not RT squared. Excellent. Okay, I'm happy with that. So this says, look at the spring potential energy just increases. Okay, the centrifugal potential energy decreases with R, and then this is the effective potential. So if you think of this as like a ball on a hill, if it starts right here at 0.12 with a 0 velocity, then it would roll down the hill and then up here and then back and forth, and we can model that. Okay, so how do we model that? Let me just real quick jump over here and remind you how to solve a differential equation. So I'm going to switch over to the paper. So here we have, I'm going to write down my differential equation. Mu r double dot equals L squared over mu r cubed minus a partial of u with respect to r. This is the same. This is the same as saying the effective potential, right? It's just I took the derivative of that one potential. So now if I solve for r double dot, I get L squared over mu squared r cubed minus 1 over mu. And then this partial of u with respect to r is going to be k r. That's that spring force. Okay, so there's my differential equation, which changes with r. So I can calculate, I'm going to break this into tiny time steps and calculate r double dot. And then I can say r double dot is equal to the change in r dot with respect to time. So it's going to be r dot 2 minus r dot 1 over delta t. If I solve this for r2 dot, I get r2 dot equals r1 dot plus r double dot delta t. This is the Euler method. This is the lowest, the second order Euler-Lagrange, Euler method for numerical calculations. So it's not the best, but it works. It worked just fine. So that gives me the velocity at the end of the time interval. Then I can do the same thing with position, saying r dot is delta r over delta t. That's r2 minus r1. These are times, not r1 and r2, because I've already switched to the one-dimensional thing. And then I can solve that, and I get r2 equals r1 plus r2 dot. This really should be r average, but I'm going to use r2 because I just calculated it. So here's the thing. I'm going to calculate r double dot. I'm going to use that to update r dot, and I'm going to use that to update r, and then I just go back up here and keep doing it forever. So let's do that. Okay. I'm trying to think how to plot. What I want to do is just add a dot here to the total potential as a function of time. So that I'm going to leave that graph like it is, and then I'm going to put another graph for the. And it'll be red, and I'll redo the red, but I'll include a dot on there, so it'll rotate back and forth. Yeah, let's do that. Okay, so down here, I'm going to say, oops, I need to switch back. You got to tell me that. I'm not paying attention. There. Okay, and I should make that a little bit bigger. People complained about this not being big enough. So, is it bigger? There. Is that too big? That's good. Okay, so I have r. I just need time. T equals 0. Let's put dt equals 0.001. I don't know if that's possible. I also need r. I have r. R is 1.2, but I need r dot. R dot is 0. I already said r dot was 0. So now down here, I'm going to say while t is less than, let's run it for 5 seconds, rate of 1,000. So this is don't do more than 1,000 calculations per second so that we can, 1,000 loops per second so that we can do it in real time. Now I'm going to calculate r double dot, r dd dot equals, I'm going to type in the equation that I have. So it says L squared divided by mu squared times r cubed. I'm going back to r, right, because I want to plot that r. And then I'm going to say minus k times r divided by mu. Now I'm going to use that to calculate r dot. So r dot equals r dot plus r double dot times dt. And then I'm going to use that to update r. R equals r plus r dot times dt. And then need to update time. T equals t plus dt. Now I'm going to plot the potential. So I'm going to say u. Let's just copy all this. Okay, and then I'm going to change that to r's, not rt. And then I'm going to plot it. And up here, I'm going to say dot equals true, comma. I think this might make a. I think this is going to make a weird line. Let's just copy it. Let's do this. Let's make 2 of them. And call this one FU2. FU2, right? So I'll have FU and FU2. Down here. Now I'm going to plot that. So FU2 dot plot is time. No, I need R. And U. T, add a T. Okay, I think this should work. Let's see. Oops. What the heck did I do? Where did it go? Window. Did I close it? I was in Safari. Window. 2-body problem. Rotating spring. There it is. Sorry about that. Okay, so now I'm going to run it. I should save it. Save, run. That's pretty cool. I like that. Look at that. Okay, let's copy this and let's make another version. What if I wanted to make a trajectory of this, plot this in real space? So up here, let's go up to the top and let's just save it and copy it. And then, oh, I didn't like that. There we go. And now down, what I want to do is I want to plot x versus y for the reduced mass. Okay. So if I want to get down here and plot x versus y, so let's just let's change this graph to x versus y. So it's going to be x title. Let's just do it x, y title equals, so it'll be a trajectory. Y, how do I get to that? Now these things I don't need. Let's just turn off all these. Let's just delete them, because what the heck, right? Don't need that. And this is called F1 equals G curve. Color equals color dot green. Blue, 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 blue. I don't need a label, but I do want the dot. Dot equals true. Okay, this stuff, don't want that. This stuff, I still want to make the same calculation. I can calculate potential, but I don't want that. I'm going to now I need to calculate R and X. So I can say X equals R times cosine theta. Y equals R times sine theta. But again, I have a problem because I don't know theta, right? So I need to come up here and pick a theta. Theta equals 0. Now I can calculate theta dot. This potential stuff doesn't need to be in there anymore. So I can say theta dot, where'd it go? Theta dot is based on L. Theta dot is equal to L divided by mu times R squared. So now I know theta dot, I can update theta. Theta equals theta plus theta dot. Dot times dt. Now I can calculate x and y, and now I can plot x and y. F1 dot plot x, y. I updated time. I think I technically did. I should move this time down the bottom technically, so let's do that. And don't indent it. Okay. Now I'm going to run it. I should save it. Now run it. Check that out. Oh, it's got a little dippy in there. I think that's just I think my time step's too big. Let's make this that. It's still got a dip. Oh, I wonder if that's real or not. I thought it'd be an oval, but seems legitimate. Okay, that's fine. So you can change the initial parameters and everything should still work, and that's what makes this cool. Now let's make one more quick model. Trinket. New trinket. And yes, I'm going to give you both the codes. Oops. No. New trinket. Let's see how fast I can make this one. I do need some of this stuff. Let's just copy this initial stuff. Actually, I don't need all of this. But then I don't have to retype it. And let's say ball, spring, Newton, because we're using Newtonian mechanics. I don't need that L. Okay, so let's make, let's say ball 1 equals sphere, position equals, I already have that R1, see, hint, I did a good job there. Radius is equal to, let's see, so it's 12, let's say 0.02. Let's make this one cyan. And then make trail equals true. And then I can get ball 2 is a sphere. Position is R2. Radius is smaller, 0.02. 0.01, and it'll be yellow. Make trail equals true. Let's run it. That's a little big. Let's make these a little bit smaller. So let's make this one 1 and 0.5. But I could play around with the sizes forever. That's a little bit better. Okay, now for the spring, connecting them, I'm just going to actually connect them with a cylinder. So let's say spring, and you could make a helix. I just don't, it's a little bit more complicated. So it's a cylinder. The position is ball1.pos. The axis is equal to ball2.pos minus ball1.pos. And then the radius is going to be equal to 0.001. And I'll leave it as just white or gray, whatever color. That looks good. Okay. So we're moving right along here. Now I need the momentums, which I already have as vector, right? So I'm going to say ball1.p equals p1. Ball2.p equals p2. R equals ball2.pos minus ball1.pos. So now R is a vector from ball1 to ball2, and I need that to calculate the spring force. But I think I'm ready to go ahead and make my loop. So let's say while I need t equals 0, dt equals 0.001 while t is less than 5, rate 1,000. Actually, I had that smaller, didn't I? Yeah. Okay, so the first thing I'm going to do is to calculate the force. So I'm going to redo R. R equals ball2.pos minus ball1.pos. And I very well might make a mistake here. So say F equals negative K times mag R times norm R. So mag R is the magnitude of that vector. I don't need to do that. I can just say times R. Let's see, so R is that way. Yeah. And so the force, this is the force on ball 2, right? So let's go ahead and update the momentum of ball 2. Ball2.p equals ball2.p plus f times dt. And then ball1.p equals ball1.p minus f times dt. Because the force on ball 1 is the opposite of ball 2. I don't need to recalculate it. Now I can update the positions. Ball1.pos equals ball1.pos plus ball. I should have shown this in numerical calculations, but I've done it so many times I don't want to do that. Ball1.p times dt divided by m1. I didn't associate that with the ball, so it's just m1. Ball2.pos equals ball2.pos plus ball2.p times dt divided by m2. And then update time. Oh, I need to move the spring too. So spring.pos equals ball1.pos. Spring.axis equals r. I already calculated r. T equals t plus dt. I mean, is this going to work the first time? Because I went through that pretty fast. If that works the first time, then you guys have to like give me an extra thumbs up or something like that. You know, make another YouTube account just to give me a thumbs up, because that's impressive. I mean, it looks right. Is it? Yeah. So that graph is weird. Then why was that graph? See, that is what I would expect. I think that's good. I'm pretty happy. Let's see. Let's give this initial. Let's do this. P2. Let's do this. Ball2.p equals negative ball1.p. Right? That we have to have the momentum constant. And now this one I'm going to give. So ball1.p is this p1. Let's give it that's in the negative. So let's give it a negative negative 0.1 times v1. Is the R changing? Is R changing? Yeah, it is. Right, because we're looking at this. It looks like you're looking at an angle, but you're not. So see, this is good. I think this is good. I think I'm happy. Now, I'm going to leave you with one homework. And that is to plot. I guess I should do it. Let's plot the potential. Okay, let's plot the potential as a function of time and see if we get the exact same thing that we got before. So let me put this back at 0 and run it. And then go over here. And I just need, where was it? Oh, it was a previous graph. Ugh. Let's see. I think I can open it up here. File, recent, my trinkets. No, that's last updated. Rotating spring graph 1. Okay, so let's just do this. And then put that down here. Let's do it right here. That's my graph. And then I need, let's do F2 with the dot. I'm just going to do F2. Right here. And then I'm going to come down here. I need these things. Which I didn't calculate L. Oh, I did calculate L. Is L in there? Yes, it's there. Okay. So now down here, I'm going to add this in. And I have to fix this. So this is L. That's fine. Mu is there. RT should be R. And I am actually going to use mag R, right? Because I'm using R as a vector, so I have to take the magnitude of it. And same thing over here. Mag R. And then that's fine. And then I can plot fu2.plot mag R U. If this works, oh man, I just don't know. I don't know. I feel like it's not going to work. What the heck? Look at me. Go me. Check that out. And so I get the same potential plot, and I didn't use the one-dimensional thing. I used actual Newtonian mechanics with 6 degrees of freedom right there, and it all worked. Okay, I better stop before I break something, and I'm pretty happy. I'll include a whole bunch of links down below, and I hope you enjoy this. I had fun, and that's the number one thing, is that I have fun. I mean, if I can't have fun making stuff, then why would I make it? And if you like it too, that really makes me happy. So I hope you like this. I'll talk to you guys later.